yours, I guess. Yeah.
Nice, thank you. And first of all, thank you for having me. So I'm also excited to share these ideas we have. And as I understood now, the questions will be in the end. So, but when there is something urgent, please write something in the chat. I'm happy to answer them. So, what will be the talk about? So, of course, the title is Generalization at of the Edge of Stability. But what I will do is I will first introduce something about generalization up to this point because I'm not sure if everyone is familiar with statistical learning theory. Then I will introduce a bit the edge of stability phenomena and what are the consequences. I will go through it and then what is our motivation and why we wrote this paper. We go through some theoretical background, then present our main results and also some empirical results, and then hopefully we have a great discussion in the end. So this is the paper I'm talking about, and before I want to start, I want to thank my collaborators. I think some of them are here today. So first of all, Jenna, which is also a PhD student at Imperial College, then also Umut, my supervisor here at INRIA, and last but not least, Tolga, my supervisor at Imperial College. So we all together wrote the paper. So every idea I'm presenting was a combined work here. I want to start the talk with this slide and with this picture, and I think it will not tell anything, but the basic idea of this talk is that in the end, when you see this picture, you have an idea what is going on. Okay? So don't think so much about it. At the moment, it can be only like a fancy picture. But in the end, I will show this picture again, and hopefully then you have an intuition what is going on, because in this picture, we basically describe everything which is going on in the paper. So I start what we want to study, and we actually want to study generalization. And what do we mean by that is what we do in practice when we have a neural network, we train it on a fixed number of data points. And then we want to know how this model works for unseen data. At the moment that is typically done, we have like a test data set and we test it. But we don't have really guarantees how this model will work, how it will do in practice, how it behaves for weird data. We don't really know it. So the question here is really, can we say something about generalization of those models? So this is like an abstract picture, but this is the basic idea, what we want to study, how we do formalize stuff like that. So in generalization, the classic view is always that we have kind of a data point which is like an element of some x and a y, and you can think about it. The x is typically like features, yeah, and y are labels. And what we think about is that this data point is drawn from some distribution, which we of course don't know. That is basically what we want to learn in the end. And what we have access to is like n data points coming from this distribution. This here means it's the product measure. What it basically just means is that those samples are drawn identical in independent distributed. Yeah. So we have access to this training data. How we formalize then a neural network? So we have some parameters and we have a predictor which is parameterized by those weights. And then we define once the so-called risk and the empirical risk. And the risk is basically what we actually want. We want to minimize the expectation over a distribution we don't have access to. And as a surrogate, we look at the empirical risk because to that we have access to. And that is what we in practice minimize, right? So we minimize it with Adam, SGD, all those fancy algorithms. We try to minimize that. And now statistical learning theory is really about saying something about this gap between those two. Here we have an integral over all possible data points, and here that is our surrogate, what we actually minimize. And when this gap is small, we say the generalization gap is small, and that is the main quantity of our work, and typically in statistical learning theory. I want to introduce a bit more about statistical learning theory and what is like the classical view and what it was for years, and why there is a huge problem. So it was shown when we have like a finite fixed hypothesis set of weights, which somehow parameterize your predictor function, then and the loss function is bounded between 0 and 1. It doesn't matter. It doesn't have to be between 0 and 1, but let's say assume it. Then in high probability, exactly the gap between those two can be bounded in terms of that. So the interesting thing here is already, okay, we have a gap, so we know something about it, so we could stop. But the problem is that current neural networks are completely over-parameterized. And here on the right-hand side, when we look at this bound, we see here the cardinality of this finite set. And those bounds can be easily extended to infinite cases. Two main references here are from Wapnick and Charlev-Schwarz, which basically bound this then in terms of covering numbers. I will not go into detail, but the problem here is that the classical view tells us that this here scales in some sort with the parameter count. So it tells us the bound isn't really tight because we know that over-parameterized models at the moment, they work pretty well. So this classical view of overfitting doesn't really apply. So there is this limitation. So generalization, how we can explain generalization in an over-parameterized regime. And that is what is studied now in the modern view of learning theory. So the key insight is what is now different to before is that the learned weights, which parameterize your function class basically, they are not fixed in advance. They come from a learning algorithm. And when we think about the theorem before, it's completely agnostic to the learning algorithm. It basically holds for everything. So that can't be true. We somehow have to incorporate the algorithm. So the classical view is wrong in the overparameterized regime. Now we incorporate the algorithm in the new learning theoretic setting. And that, I would say, is the modern question. Which properties of this learning algorithm, so the weights I get in the end, actually help, or how do they explain that this generalization gap is small? And does it even explain generalization in the overparameterized regime? So generalization in the modern view, and just want to give a brief overview for those people who don't know it, can be divided in some approaches. And the thing is, the problem becomes way more complex when your weights actually depend on the data, as they do here, and on some algorithmic noise, maybe mini batch sampling, right, as a typical algorithm. This problem becomes way more complex. And typical approaches are, for instance, algorithmic stability, which studies if an algorithm, how it behaves. When I change a bit the data set, maybe the loss stays stable. So those kind of ideas, they go back to the 70s, but what was really formalized was 2002. Then there are information theoretic approaches, and there's also the typical Puck-Bayesian view, which looks at the final weight, which is like kind of a randomized predictor here. And all those approaches actually led to incredible nice bounds. But there's at the moment a common theme that good generalization measures are nowhere to be found. That's a problem, even though those new approaches, we incorporated the algorithm in learning theory. There are now prominent examples. They show maybe flat minima, for instance, might be the reason why a model generalizes so a flat minima is better. Some sort of sharpness measure, so like the trace of the Hessian might be a good generalization measure. Also some spectral norm-based measures. But in the end, there are many papers which show when I try that for different models, there is no generalization measure which really works, even though we already improved the learning theoretic setup. So there's a different line of research, which basically is a bit grounded also in Umut's work, who is here today. So maybe when I look just at one set, just of one weight point, like maybe the final iterate or something, it might be not enough information to say something about generalization. And maybe we have to look like over the trajectory or more weights to say something about the generalization performance over models. So instead of studying the single output, the learning algorithm is now viewed as something which gives you back a random set. That sounds really abstract, but what you can think about it is, for instance, you have a training algorithm, and at each iteration, you basically get a new weight set, a new weight configuration. And you gather them all together and then look over all those weights, how they behave. Maybe you can say something then about generalization. And the really relevant quantity here is then the worst case generalization gap. So we want to bound still this quantity of risk minus empirical risk, but this time we look uniform over a set of weights instead of just one single iterate. And then we hope, okay, maybe this viewpoint gives us more information and we get better generalization bounds and even better generalization measures. So this view is quite complex. So there was some progress, for instance, which showed basically worst case generalization gaps in this kind of form. I will go here into detail. So what it says is basically we have here a quantity, which is like a complexity measure of my random set, which I can think about in a like as a trajectory. And then here's an information theoretic term, which is interesting because we can't bound it really, but it doesn't play a huge role at the moment. And so we get still a bound, and we have a lot of complexity measures here, right? So there were, for instance, Tolga introduced here the persistent homology dimension. Later papers by Ben and Andreeva used some topological quantities here to bound the generalization gap. And they all showed they correlate well, basically, with the worst case generalization gap. Here also to mention for people who say, okay, what is about this IT term? There was a recent paper which basically got rid of this IT term using some stability ideas. But it's rather a technical framework. But what it shows here is we also get a complexity measure over the set here, which you can imagine is just the trajectory. So when we have this, so we think about the trajectory, and I wanted to convey the message, okay, it really works in this sense. So what was shown in recent papers is when I look about when I look over topological quantities of this trajectory, so don't care so much what they are, so they are some kind of topological signature, then it was shown they actually correlate pretty well with the generalization gap. But when we think even more about their experimental setup, the interesting part was that they used the last part about your trajectory. So like the final iterates when the model already converged. And that is a bit weird because it means that when I'm at the final stage of my training and I look at the trajectory, let's say like 5,000 iterations, there is such a topological structure which correlates with the generalization gap. What the key message behind this is then, okay, late stage trajectory of an optimizer exhibits strong topological signatures. But such signatures would be somehow absent when a model would converge just to a single minimum. Why is this the case? Because when I would converge and then look at the trajectory, I basically have in my set always the same point. And that would not give me any topological meaning, but apparently it's not at a single point. It does something such in a way that there is topological structure. And it raises a fundamental question. Why does this happen? Why does this late stage of training, when we go through the weight space, why is this topological meaningful? And are not simply sitting in a minimum and we shouldn't observe any topological structure anymore because we are basically in a fixed point? So to explain, this is a central question. Why does this happen? So we go to a different line of research, which is basically called the edge of stability. So the edge of stability phenomenon comes also from earlier ideas, but I would say a really good paper about it is from Jeremy Cohen. And what it says is when you train a neural network here with full batch gradient descent, it tells you when you look at the largest eigenvalue of your Hessian, right, of your empirical risk, when you look of the loss, when you look at the largest eigenvalue of the Hessian, then what happens is that this eigenvalue increases, 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 and then fluctuates around some value. And this value is typically 2 over the learning rate. So when I have learning rate 2 over 20, then 2 divided by this here. This is always the threshold. And why is this interesting? Because it means when you hover over this threshold, normal optimization theory would tell us the dynamics diverge. So when you have a quadratic function and you say your Hessian has the largest eigenvalue, 2 over the learning rate, and is larger than that, then your dynamics would diverge. But in neural networks, it seems that the loss still monotonically decreases, even though it wiggles here around, but the loss gets smaller and smaller, even though when we are over this kind of stability threshold. And he termed this phenomena edge of stability. Yeah. So something is going on here. Kind of our dynamics is not really stable, but still the loss decreases. It's a huge area of research, and people are trying to figure out why, for instance, this oscillation happens. They used, for instance, Taylor approximations to the third order and showed that might be a reason. But what is still an open question today, so at least I'm not aware of like a of a good reason, why actually the sharpening happening, why it happens, why this increases. We don't know it. Yeah. But just that you have in mind, so the edge of stability phenomena means that the largest eigenvalue of the Hessian hovers over this threshold. And this threshold is interesting because it implies that your dynamics is unstable. So here again, a bit summarized. So we know, okay, during training, the sharpness progressively increases until it approaches a stability threshold, which is 2 over the learning rate. So the largest eigenvalue does that. So classical optimization theory predicts your divergence once this threshold is crossed. However, this somehow doesn't happen. So there raises a question, what does this imply, right? And I think there is a beautiful connection to chaos in this sense, because when we know, for instance, for gradient descent, when we linearize it and look at how it is, how it behaves under different initializations, basically, we can see that the edge of stability, when the largest eigenvalue is over this threshold, it implies basically that the top Lyapunov exponent is positive. That is the main point. And that is for dynamical system people really interesting, because when the top Lyapunov exponent is greater than 0, then it means that those trajectories actually diverge exponentially. So it means this dynamics has to be divergent. But there is one thing where it doesn't happen. So okay, so normally it would diverge, but it wouldn't diverge when it stays in a bounded region. And there were papers showing that this might be the case. For instance, a good paper of Suvritzra, who was showing that for gradient descent, when you have a forward invariant set, then gradient descent doesn't diverge. It stays in this bounded region. But it raises a fundamental question because it means, okay, we don't converge to a point. We kind of just staying in a bounded set. So and that raises our motivation. So we have like, okay, we have large learning rates during training. We see it improves somehow generalization. We have a chaotic training dynamics because of this phenomenon of edge of stability. And somehow we are not then converging to a point. We are rather converging to an attractor, which is the term for it. And the trajectory, how work was doing it before, seems really informative. I wrote it twice, sorry about that. And that raises a question, how can we explain generalization in this chaotic regime? So all those points we know, and this paper tries to bring them together. Yeah. Here on the right, you see, for instance, a picture of an attractor where we use this dynamics and run it with SGD, and we see it doesn't converge to a point. It actually goes infinite many times in this bounded set. Yeah. So here another example, there's for instance the Hoover system, which has like a beautiful attractor, which is kind of a fractal, and here the system before, which is here looks like a bit like a chessboard, the attractor. So they can be fractals, they can look really curious. Yeah? So the main question is now, okay, we know trajectories are interesting. We somehow have a feeling that those dynamics don't converge to a single point. They stay in a bounded region, which we call attractor then. Which theory helps us to somehow specify this attractor set, and how can we incorporate it in generalization? So to do that, we introduce here a bit random dynamical systems. I know it looks a bit harsh, but I will explain it on a simple example. So a random dynamical system also considers always has two main components. That is one, the metric dynamical system, which is basically like a machine which gets you the right index. And then a measurable co-cycle, which is typically kind of can be considered as like your update map. Yeah? Will not go into detail here, but when you have later questions about it, I will go here back. So to make it more intuitive, what a random dynamical system is, and for instance, that SGD is one, right? There are many examples. You can basically write everything as a random dynamical system. So we have like noise, which are like my mini batch indices. And you have to imagine it like you have like an infinite sequence. So you draw them all at once, and then you fix this noise sequence. So you have like all mini batch indices when you, for instance, run an SGD. Then you have your metrical dynamical system, which is here kind of just a shift operator. So what it does is it always, off this infinite sequence, it gives you back at the right time the right index. And you have to imagine it when you run SGD. At the first iteration, you use this index. In the second iteration, you use this mini batch index. And this is just a way to formalize it, that at the time you get the right index. Then your measurable co-cycle from the definition before is then your update map here for SGD, which can be written in this way. Yeah. And then you see that when you run SGD t times, it can be it's just a composition of the first step update map, where at the right point where you take the correct index. Yeah. That is maybe gives more intuition what a random dynamical system is and how it relates to machine learning, for instance, in SGD. So now I already told you that it might be not the right way to look at a single fixed point, because we know we are in the edge of stability, this dynamics becomes wild, and we are not converging to a point, we stay in a bounded region. So what is the formalism for a random attractor then? So a random attractor has basically two main components. So one is it is invariant. Invariance means basically when I apply my set, so it's the image of this function, then I stay in the set. Yeah. Here again, because this here is all a random set, so it depends on this noise omega here. So we need here the right index again. So think about again about SGD, it's just shifting the index, it just gives you the right index. Yeah? And then we define like attraction in a pullback sense. Why we do that? So when we normally think about it, what means attracting, we compute it in a forward sense, right? We go to infinity and then see where our dynamic stays in. And here, when we talk about random dynamical systems, we have to do it in a pullback sense, because at each iteration we're adding noise, right? So our set doesn't stay stable, it's dependent on the randomness. And to account for that, we basically go back in time and have the attractor and pull back. Yeah. Also here, when you have later questions about it, please let me know. But it's just a formal definition how I define a random attractor. So again, one step back. So we have the random attractor, and now we want to relate that somehow to generalization. So we want to know how the generalization gap can be controlled over this set. We know the edge of stability phenomena, and what we do in our work is basically taking the idea of Lyapunov exponent that this is positive and taking the idea that the largest eigenvalue of the Hessian is 2 over the learning rate, and we define then for our random dynamical system, which I can think about in SGD, and we define the sharpness of order k, which is composed of the spectrum. So what we have here is the Jacobian of our update map. So typically it's just like the identity minus the step size Hessian. For instance, in gradient descent, then the noise would be constant. For SGD, it's still the identity minus the step size, but this time it's the Hessian, also the mini batch Hessian. Yeah. So the RDS sharpness, we define it then in a way. So we're taking the expectation over the algorithmic randomness, which comes from this infinite sequence of mini batch samples. Then we're taking it uniform over the attractor set here, which is also dependent by the noise. And then here we're taking the singular values of our update map. Yeah. So it's really a quantity which is determined by the singular values of the Jacobian of our update map. Yeah. And this is the main quantity which we use then to define our new dimension. Here again, just in the deterministic case, you can think about that our randomness, so the mini batch samples are constant. And in SGD, you just have the indices which you sample. Yeah. Again, the classical sharpness is the largest eigenvalue of the Hessian, right? So what we look at is the singular values of the Jacobian of the update map, which is identity minus learning rate Hessian. Yeah. So what we define with that is a new term of dimension. So we have now our sharpness coefficients of order k, which are determined by the singular values of the Jacobian of the update map. We order them, yeah? And then we look at the index here. So what we can see is it's the maximum index such that when I sum up my sharpness coefficients, such that they stay positive, yeah? So, and then the rest will be compactified in a fraction. And that can be seen as like a non-integer dimension or a fractal dimension, right? So it consists of an integer part, which comes from here, and some fractional correction, which is smaller than 1. Some intuition about it is it's kind of an effective volume of the attractor set. So it measures how many directions are expanding, and that in the whole picture also in how many directions are contracting. Yeah. Similar notions, maybe someone of you is familiar with that, were discussed by Kaplan-York and also Hunt, for instance, in the 90s, in the 2000s. Yeah. Yeah. So that is our sharpness dimension. And what we show now, and that is really interesting, is that we can relate this to the generalization gap. So again, it's like an informal statement. I will not frame all assumptions, but basically there is some regularity on the dynamics. We have a bounded loss and a Lipschitz. Those two are typically standard assumptions in learning theory. Then we can say in high probability that the generalization gap, the worst case generalization gap over the attractor, is bounded again by some sort of mutual information term, which I will disregard for a minute, and this newly dimension. And the interesting thing is, such results could be also obtained, for instance, in the Minkowski dimension, and we believe that fractal dimensions are lower dimensional than like just the parameter count. But in this case, we really know, since when we go back to the definition, and we are at the edge of stability, that at least, because edge of stability per se says first only one thing about the largest eigenvalue, we know lambda 1 is smaller than, lambda 1 is bigger than 0. So we really know that this dimension has to be smaller than the ambient dimension. So this quantity is then provable lower than the ambient dimension. And that is interesting because it explains us why it might be that generalization is not determined by the parameter count. It's determined by an intrinsic dimension, and especially when we observe edge of stability, how we do for neural networks, this quantity is small. Yeah. So I might not go through, how's the time? It's okay, I guess. So I might not go over the proof sketch, but the main point is that we actually show that the Minkowski dimension is bounded by our new sharpness dimension. And what we do is we really use the structure of the attractor set. So such a bound wouldn't be obtainable when we just use some subset of the weights, as it would be as it was done before. Yeah. So we really use the structure of the attractor set and especially the invariance property to get such a bound and then obtaining our main result, which shows, okay, the generalization gap over this attractor set is controlled by this new dimension. And then especially in the edge of stability, this quantity is smaller than the ambient dimension. So that is the main message here. We go a bit back to we go back to some experimental results. So of course we want to know now. So we obtained our generalization gap here. We obtained this quantity, and now we want to see if it actually says something about the generalization gap, also empirically. So we have the generalization gap, which is here basically defined as the absolute difference between train and test accuracy. So to that we have access. So we have some test set. We train the model. We look at the train loss. We look at the test loss, and then we look at the difference to estimate our generalization gap. Something about the coefficients. So I think the Kendall-Tau coefficient is quite clear, and but maybe the granular Kendall coefficient a bit to understand it. The problem is to do like such analysis and to see how your quantity really correlates with it. You always have to also account for that you have different learning rates in different batch size, and this coefficient was invented to account for those effects. So what are we comparing to? So we are comparing once to the typically sharpness, which is here the largest eigenvalue of the Hessian, how Cohen defined it. We look at the trace of the Hessian, which is believed to be correlated to flat minima, and which was shown also empirically that it really correlates well with the generalization gap. But Newly paper also showed that flat minima is not the whole story. And we compare it then to our RDS sharpness, once the largest one and once our sharpness dimension. And we compare it then to topological measures, which I were showing before, which showed amazing correlation for the trajectory. So there's one, the persistent homology dimension introduced by Tolga, once the alpha weighted lifetime sum, which is a building block of the persistent homology. You can choose your different metrics. So the Euclidean metric was used before. Then my colleague Ben did it for data-dependent pseudometrics, which is basically a metric based on the loss. And interesting here is they are all trajectory dependent, so they can't be evaluated point-wise. So I really need a set of points. So I have to run the trajectory as I have to run my algorithm a certain time interval. Let's say like 100 iterations, then I get 100 points, and then I can compute those quantities. We compare it to forward trajectory and backward trajectory, which basically means I train to a point and I look at the last 100, I look backward 100 iteration or forward 100 iteration. So what we do first is like just a small 3-layer MLP, because of course we have one big problem. Even though we showed that this quantity is related to the generalization gap, it's based on the whole Hessian spectrum, which is of course for bigger models really hard to compute. So we started to do this experiment small and calculated correctly our dimension to see if it correlates well with the generalization gap. And what we actually observed that we do way better than previously used topological quantities. We can even see that the persistent homology here correlates negative, but our sharpness dimension correlates here in the Grandel tau for almost 67, 76%. German, I always say it the wrong way. So 76%, yeah. So we see actually it performs quite well. We scale it then a bit up. We do the same experiment for a 5-layer MLP and also see that we outperform here. By the way, those mean that is here, for instance, stochastic Lang's quadrature. So it is a method to make this a bit more computable. I will not go into detail here, even though I think, I don't know if Chenna is here. So, but he knows, well, he knows better about that than I do. So, and then we scale it up to a 5-layer MLP. And then we wanted to make a test, which is basically, there's a phenomena which is called grokking. And what it is like sudden generalization. So even though your train loss goes down, no, the other way. The train loss goes down, but your test accuracy is also low, and then suddenly, no one knows really why, suddenly your test accuracy goes up. And that you call then grokking, this phenomenon. And we wanted to test how our dimension works in this setting and if it actually predicts kind of grokking or has the same behavior. So we do a simple experiment, how people do when they test grokking on this data set here. And we do it for a 2-layer MLP and a 3-layer MLP. I'm aware it's kind of small, but we see that we scaled our, we will see later that we also scaled our experiments up. So what we see here is one for the 2-layer MLP, and we actually see that also the sharpness and the trace are doing well, but also our quantities actually correlate pretty well with the phenomena of grokking and the generalization gap. So to make it more precise, for instance, in this example, we see the sudden jump, and we also see how our sharpness dimension drops. So the interesting part is, so we're generalizing better. That basically means that our dimension drops. So the weight space lives then in a lower dimensional set. Yeah. So similar can be observed for different experiments. I will not go into detail here. So, and then for the 3-layer MLP and so on. So we now wanted to try to scale up those experiments because in 5-layer MLP is not what people use at the moment, and they use more like billion parameter models. We can't scale up to that, but at least we scale up to 120 million parameters, I think, no, 112. So we use methods to somehow get the spectrum of the Hessian, and we use for that stochastic Lang's quadrature. And what we can see here, for instance, is SGD on GBT2. So we get at least the density of the whole spectrum. And then we run those experiments for SGD, once for SGD and Adam, and we see that our quantities are correlating quite well, while for instance, the persistent homology and the alpha weighted lifetime sum, which were proposed before, and actually also requiring a trajectory, which is not easy to store and which you don't always have access to, are negative correlated, while our quantities stay positive quant. Yeah. So I want to show again this picture because that's how I started my talk. And now I hope you have a better intuition, but I go back to this. So we are in the weight space. So we're running our algorithm. Then we know through the edge of stability that we have like expanding directions. So the largest eigenvalue of the Hessian expands, which would mean divergence. But we also have contracting directions. And actually, the interplay between those are the reason why the weight space in the end lives in a lower dimensional set. Ah, there's a message. I will answer it in a minute. So what we see here, okay, the weight space actually lives in a lower dimensional set. So our sharpness dimension, especially in the edge of stability, is lower than the ambient, smaller than the ambient dimension. Oh, so the conclusion what this paper does, so we know neural networks train in the edge of stability, for instance, for a full batch gradient descent. We connected it to generalization theory, We used for that new tools, random dynamical system. We connected to the geometry of the random pullback attractor, showed that this is lower dimensional, especially in the edge of stability. And we introduced a new dimension called sharpness dimension, which correlates typically better than previous results. I want to say thank you once, of course, to my collaborators, and once to those two teams I belong to. That is one, the Sierra team, and especially I want to thank Umut here, my supervisor. And then on the other hand, the Circle group, where here I also want to thank Tolga, my supervisor, and Jenna, who was also co-author on the paper. So, and that's it. So thank you a lot. And when you have questions, please ask them. So I might